Hello. This video will provide a simple example of the OmnIoT SoftHub communicating with the cloud-based Ubidots dashboard. We'll quickly run through our example and then give a high-level overview of the SoftHub configuration file that was actually used. In the video description, we'll provide a link to a brief write-up covering the details unique to connecting to the Ubidots platform. But please note, this video is not meant to be a full how-to tutorial. We're assuming you have some familiarity with the OmnIoT SoftHub platform, the Ubidots platform, and MQTT in general. If not, there are links in the video description providing lots of additional videos and documentation to get you started. And while this video only runs through a quick demonstration scenario, we've also provided links in the video description to download all of the configuration files that are used in the example as well. Note also that in the interest of brevity for this example, we're going to keep things as simple as possible. Both the OmnIoT SoftHub and the Ubidots platforms provide far more functionality than we'll cover here. But this video should give you a good starting point to begin building your own SoftHub Ubidots IoT dashboard applications. For our example scenario, we have the following: a Vernier GDX-TMP Bluetooth low-energy temperature probe sensor, and a Raspberry Pi Zero running the SoftHub daemon. We've also attached a breadboard to the Raspberry Pi Zero where we've connected a button and an LED to two of the Raspberry Pi's GPIOs. Our example scenario is quite simple. When we start the SoftHub daemon, it will connect to the GDX-TMP sensor and start publishing the reported temperature data via MQTT to a Ubidots dashboard that we've configured. If the temperature goes above 30 degrees or below 10 degrees Celsius, we consider the temperature out of range and an alarm is triggered. Once triggered, our alarm is configured to send us a warning email and to also light the LED on the breadboard. On the Ubidots dashboard, the temperature gauge text will also toggle from green to red. Each time it's triggered, the alarm will disable itself for a period of time to ensure we don't get a flood of emails. Normally, you would have this alarm disabled for some significant amount of time, but for our video, we've set it to disable itself for only 30 seconds so that we can run through the process of triggering and clearing the alarm a couple of times. Lastly, the alarm can be acknowledged by turning off the LED either locally using the button or remotely using a control widget we've configured on the Ubidots dashboard. So let's start. Holding the temperature probe in hand should raise the probe temperature fairly quickly. Notice that just as the temperature exceeds our upper threshold of 30 degrees Celsius, the LED is lit and we receive our warning email. We'll use the button on the breadboard to acknowledge the alarm and turn off the LED. Despite the temperature still being over 30 degrees, we don't receive any additional alarms while the alarm is disabled. Once the disable alarm timer expires, however, the alarm will rearm itself and be ready to fire again. It should be noted that while our example simply lights the LED and sends an email, much more functionality could just as easily have been configured to be executed. Anything from actuating an external piece of hardware to cool or heat whatever medium the temperature sensor is monitoring, to running a script or system command externally on the Raspberry Pi. So now we'll heat our probe again. The LED lights again and another email arrives. This time we'll use the control widget on the Ubidots dashboard to remotely acknowledge the alarm instead of the button. And as you can see, we've turned off the GPIO the same as if we'd pressed the button locally. These are all the objects and rules needed to configure our scenario. From beginning to end, it took about 20 minutes in total to configure and deploy this example. Again, we're not going to go into the detail here, as all of the functionality illustrated is covered in depth in other videos. But before we close, we'll take a quick look at the pseudocode for the rule set we used to create our configuration file. Our rule set consists of 6 events we've configured and 7 rules to be evaluated. Note that with the exception of the app starting and the app stopping events, All other events are asynchronous and may occur at any time and in any order. On application startup, we'll receive an app starting event. We'll turn our alarm GPIO connected to the LED off, and we'll initialize a flag we'll use to keep track of the alarm state to false or off. On the arrival of each new packet, we'll receive a new packet event. On new packet events, we'll first always forward the packet data to the Ubidots dashboard. And then, if we're not already in an alarm state and our temperature is out of range, we'll set our alarm state flag to true, turn on the LED GPIO, send our alarm email, and start the disable alarm timer. When the disable alarm timer expired event occurs, we'll turn the LED GPIO off and set our alarm state flag back to false. When a GPIO button press event occurs, if the alarm state flag is true, we'll turn the LED GPIO off. Similarly, when a user-defined event is received from the Ubidots dashboard, if the alarm state flag is true, we'll also turn the LED GPIO off. Lastly, when the app shutdown event occurs, we'll clean up by turning the GPIO connected to the LED off before exiting. That wraps up our Ubidots example video. Again, see the video description for a link providing a write-up covering the Ubidots specific settings used in the example. And if you have any comments, questions, or suggestions, please follow up with us at www.omniot.com. Thanks for watching.